Welcome back. Now that we've seen the action potential in action and seen how graded potentials become the action potential, and we eventually have summation there to get us to that point of an action potential, now we can look at where that action potential in a sense goes as it makes its way down to the axon terminals and eventually to the synapses, where we now have the ability to communicate with the next cell that is there. The synapses themselves come in a couple of different varieties, the most common of which is the chemical synapse, and then we also have electrical synapses. And so chemical synapses are used essentially in the central nervous system, they're used in the peripheral nervous system, they're used really everywhere, and this is our primary way of communicating with one cell to the next. And essentially this is how that action potential is going to go from our presynaptic neuron and get over to that postsynaptic neuron. So rather than, in a sense, kind of having a wire, and then we have another wire that comes in, and then we kind of twist the two wires together with one another to make them to come together, like we would if we had an actual wire, and that electrical impulse can just simply go from one cell straight through to the next. Here we're going to have this little junction. We're going to have this synapse that's going to allow us to make that connection between the two cells without them actually connecting with one another. And so this gets done by utilizing neurotransmitters. And so in this particular case here, we have acetylcholine, and that acetylcholine is going to go find a receptor. So we're going to have a receptor on the postsynaptic neuron there, and it's going to bind to that, and it's going to cause that receptor channel, that ligand channel, to open up and allow then our sodium ions to rush into the inside of the cell. And this happens every single time that we have that chemical messenger utilized to cross the synaptic cleft to get us to that postsynaptic neuron. So the postsynaptic neuron does not get to be to a graded potential until all of that neurotransmitter, which is released from the presynaptic neuron, from these little vesicles, to come across and bind to that next cell. With the electrical synapse, it's more like the two wires that I just drew coming together. In this one, it's in a sense a direct connection between the two. And so we have gap junctions that allow for our ion concentrations to move directly from one to the next. And so essentially that movement of going from negative on the inside and becoming positive jumps right across to the next cell, and they start to become positive as well. And so sodium is rushing into the inside of the cell, and it's coming in from the other cell, from our presynaptic neuron that's there. And essentially the movement, that action potential, moves from the presynaptic cell directly to the postsynaptic cell with no problems. This we see really only in the brain and in the eye. And so there's a couple other places, but those are kind of the biggest areas where we use, especially in the brain. But again, the most common type of synapse that we have is the chemical synapse. And so as a neuron comes down and it has its axon making its way to the synapse, that nerve impulse travels down the axon itself. It gets to the end bulb here where we have our axon terminals there, and it causes voltage-gated calcium channels to open up. Those voltage-gated calcium channels open up. They allow calcium to come into the inside of the cell, and that causes all of these vesicles that contain our neurotransmitter to migrate to the end bulb, exocytose their contents, and then their contents comes out here and binds to the receptor. Once it binds to the receptor, that's going to open up this chemically gated channel, and now our sodium can rush into the inside of the cell. And so that can then make its way up onto the inside. Here's another one that's opened up. And as long as that neurotransmitter is bound to that receptor, that chemical gated channel is going to stay open. As soon as we start to break down these chemicals, then we're going to go, in a sense, back the other direction, and those chemically gated channels are going to close. And so that's going to then end the transmission of the signal from one cell to the next. If there is enough of summation, we're going to go from our graded potentials over to our action potential. And so that's going to make its way from there. So just kind of review what we just saw in the picture itself. So action potential travels along that presynaptic cell, comes down to the end bulb, and that causes voltage-gated calcium channels to open up. Calcium starts to rush into the inside of the cell, and this causes exocytosis of our vesicles. Those vesicles, as they open up, they release neurotransmitter out into the synaptic cleft. It binds to chemically gated channels on that postsynaptic cell, and those chemically gated channels primarily allow sodium to start to come into the inside of the cell. And then just like with other processes, potassium chloride ions are going to become involved as well as we start to depolarize the postsynaptic neuron. The thing is, though, not all of our signals from that presynaptic neuron are excitatory. And so most of the time we think of them as being an excitatory process. And so this is where, as that neurotransmitter comes into the synapse, it's going to open chemically gated or ligand gated sodium gates. And that's going to start to depolarize the cell. So we're going to start to move from our negative 70 millivolts and start to move over up towards 60 millivolts. And so we're going to depolarize the cell at that point. But we can also cause an inhibitory response. And so in an inhibitory response, we're going to have those postsynaptic cells opening things like potassium gates or even chloride gates. And we're going to go from negative 70 millivolts towards, say, negative 80 millivolts. And so the cell itself is going to become more polarized. It's going to become less or more negative, and it's going to become hyperpolarized at that point. So when we cause excitation, we have what we call an EPSP. This is an excitatory postsynaptic potential. This is, in a sense, the green light. So this is going to be turning on the postsynaptic cell. But we can also have an IPSP, and that IPSP is our inhibitory postsynaptic potential. So as we become, an IPSP causes hyperpolarization. Long word there. And our EPSP causes depolarization. And so we have a difference in what can happen within those cells themselves. And we saw this before when we looked at the reflex. And so the reflex itself utilizes both an IPSP and an EPSP in order to get movement to occur. So we have our painful stimulus here. Our signal comes in through our afferent neuron. That afferent neuron comes in. Our posterior root ganglion has the cell body. Its synapses inside the cord on a interneuron. That interneuron then stimulates two separate neurons. It is going to stimulate positively excitatory, so we're going to get an EPSP in our flexor muscle, but in our extensor muscle, we're going to get an IPSP. So we're going to inhibit that muscle. So if we need to do flexion of the elbow, we need to be able to contract our flexors and at the same time inhibit those extensors. So we're going to change the process there in order to allow us to quickly pull away from that painful stimulus, to get away from that burning pan as that occurs. And so even when we're just simply moving around doing things, we're going to be doing things like some IPSP at times, and at other times we're going to have EPSPs so that we can control the motor movement that is happening there all the time. At any given neuron, we can have any number of EPSPs as well as IPSPs synapsing on the postsynaptic neuron. So this is our postsynaptic neuron. It has a combination of EPSPs and IPSPs firing on it. There's some more over there. Some more EPSPs over here. Some more IPSPs over here even. So we got all kinds of stimulation on this one postsynaptic neuron. That postsynaptic neuron is then going to essentially, when it comes to our voltage, we're going to have negative 70 millivolts. So we'll just have our graph here, negative 60 over here, negative 80 over here. And depending upon how those EPSPs and IPSPs are coming in, our voltage may be simply just kind of doing this. We're having a little bit of excitation, we have a little bit of inhibition, but nothing really ever happens. If all of a sudden the EPSPs, in a sense, kind of start to win, then we may get an action potential. If all of a sudden the IPSPs are more so winning, then we're going to get hyperpolarization. It all just kind of depends on the overall activity of all of those potentially thousands of presynaptic neurons. And so we have that convergence on that one cell, and this postsynaptic neuron isn't going to fire off an action potential until it has just the right combination, where the EPSPs essentially outweigh those of the IPSPs. The fact that we have a synapse here, so the fact that we have a crossing between the two cells, also gives us a little bit of a delay. And so this is what we call the synaptic delay. The synaptic delay is the period of time that it takes for our two cells effectively to communicate with one another. And so as our neurotransmitter gets released into that synapse, that period of time between the synaptic release of that neurotransmitter, so the time that it takes us to release the neurotransmitter for it to kind of float across the synapse and then bind to its receptors, is the synaptic delay. So it takes time to kind of cross the gap, in a sense, versus like on an electrical synapse, there's basically virtually no delay. It's going to go right from one cell to the next. And so it has to have time for that action potential here for that electrical potential to jump the gap, so to speak. And so we've got to get those neurotransmitters into the synapse, bound to the receptors, and causing those ion channels to start to open up. And that's going to be our delay there. The more of these, there's our cell body, here's our next axon, and then our next neuron. So the more of these that we have in the pathway, the slower the process is going to be, because at each of these synapses, we've got a little bit of a delay. And that little bit of a delay adds to the period of time that it takes for that signal to get from wherever it was generated, way over here, all the way up to where we have conscious awareness of that particular stimulus, whatever it happens to be, whether it's stepping on something, cutting something, just simply touching something, whatever that stimulus is, it takes time for it to cross those synapses. So as we can see here, we can have all kinds of different scenarios as far as the pathways themselves go. We can have convergence where a whole bunch of other presynaptic neurons are all synapsing on this one postsynaptic neuron. But this neuron could go out and diverge its information and send that information off to a whole bunch of different places. So this first one here could be something like pain. And so we want to have a strong stimulus coming in about that pain so that we can send something out to do. And part of that output is going to be over all of the motor units that are involved. It could also be something like a memory of a smell or a sound, where that one input of, say, hearing a song that you haven't heard in a long time and it was from when you were younger, something like that. And all of a sudden, as that information comes in about the music, it sends out information out to many different places. You remember where you were when you were listening to the song, you remember who you were with, what you were doing, things like that. All that information starts to fire off again, and we then have, in a sense, all the memories of that information. And so that allows those synapses to send off all of that information into different directions at different times, depending upon where we need it to go at any moment. And so this ends our look into the organization of the nervous system itself, and we'll continue on looking a little bit deeper into the nervous system next time.